Let us just wait for a few minutes before starting the session to see if somebody else is joining. Uh, okay, good evening. Am I audible and is the screen visible?
Yes, you're audible and the screen is also visible.
Okay, thank you. So, let us begin today's session. Uh, So, I welcome all of you to the third live session of the course Introduction to Fluid Mechanics, being offered by Professor Suman Chakravarti of IIT Kharagpur. As in for myself, I am Abhik Deve, PhD scholar in the Department of Mechanical Engineering at IIC Bangalore, and today we shall be discussing on the problems related to the surface tension, um, as we started, which we started in the previous session itself, and then we shall go into some other concepts such as no slip boundary condition, the viscosity, and problem and some problems related to the surface tension. So let us begin without any further delay. Okay, so the first problem, we have been asked to derive an expression for the pressure difference across the surface separating two fluids. So how to go about it? So this essentially will give us the pressure difference across any two across a surface that is separating two fluids. The two fluids on the two sides may be same as each other, or they might also be different. So like a soap bubble or a water bubble, so a water droplet. So in a water droplet, the membrane that is separating the water from the air, um, we can find the pressure difference across these two um, mm, uh, fluids. And say in soap bubble, so the inside also there will be air, and outside also there will be air. So calculating the pressure difference across the membrane of the soap bubble that separates these two fluids, which are essentially the same here. So mm we will take a section of the membrane in this case. So this is the membrane, and uh, let this angle be d theta 1 and d theta 2, and this be r1 and this be, so this is r1, uh, this one, and this is r2. Okay, so this side is liquid, and say this side is air. So there is a pressure from the top, which might be essentially the atmospheric pressure P naught, and from inside there is another pressure, or whatever the pressure difference we will calculate here. We are considering that the surface tension between these two fluids, and that is the liquid and the air here, is sigma. So the surrounding fluid here is air. Now we will first take this the section which makes an angle d theta 1. So if we see it here, if we enlarge it, what we will see, so basically we are taking this section into and we are enlarging it. So d theta 1, this angle is d theta 1, and half of these angles, that is each of these angles, will be d theta 1 by 2, and this angle will also be d theta 1 by 2. Now this angle, so this is essentially a perpendicular drawn here, that is perpendicular to the surface, which has been extended here. So if this angle is d theta 1 by 2, this angle will be uh, 90 minus d theta 1 by 2. Okay, and this length is r1. The surface tension, so from the top, the surface tension, it is pulling the surface like a stretched membrane. So we draw the surface tension vectors here, so it will be something like this: sigma in this direction, and it will be acting on this sigma, it is acting on this length. So this length is what? It is d theta 2 r2, and similarly on this side it will be sigma d theta 2 r2, and there will be, and again the surface tension will also be acting on this sides, so this is acting on this line, so this will be sigma d theta 1 r1, and this is sigma into d theta 1 r1. Okay. So now so if we see, draw the forces here, it will be sigma r2 d theta 2 and sigma r2 d theta 2. Similarly, so we were drawing this this side as here. Okay, wait. So this surface we have drawn here, and if we draw this surface now, what will we get? It will also be similar. So tangents at the surface. So this is essentially this surface, the one with r2 and d theta 2. So this is r2, this angle is d theta 2, and half of this angle will be d theta 2 by 2. This is 90 degree, so this angle will be d theta 2, 90 minus d theta 2 by 2. And what will be these forces? These forces will be sigma into r1 d theta 1. This is sigma r1 d theta 1. Now, so if we see the forces, um, uh, and we try to balance the force in the vertical direction, then see a component, this sigma r2 d theta 2, a component of this, that is sigma r2 d theta 2 cos 90 minus d theta 1 by 2 will be acting in the vertical direction, something like this, of both these forces. Similar is here also. Sigma r1 d theta 1 cos of 90 minus d theta 2 by 2 will be acting in the downward direction. So if we try to balance the forces in the vertical direction, so balancing the forces in the vertical direction, uh, so if we take the components, so there will be two components of sigma r2 d theta 2, that is there are two forces each equal to sigma r2 d theta 2. So we can write it 2 multiplied by this one sigma r2 d theta 2 and the cos 90 minus d theta 1 by 2. This component of the force is acting in the vertical direction, in the downward direction, plus similarly to from here now sigma r1 d theta 1 and the cos 90 minus d theta 2 by 2 component of force component will be acting in the downward direction, and this will balance the let the internal pressure we have the internal pressure of the fluid is considered here to be let's say it is pi. So pi denotes the internal pressure and po denotes the outside pressure of air. So these two downward forces will balance the net vertical upward force, and the net vertical upward force will be pi minus po. This is the pressure difference delta p across the membrane, and this is acting on the entire area of the membrane that we have considered. So it is each side, the sides are equal to r d theta 1 and r d theta 2. So if it is like a square section, it will be the area will be r d theta 1 multiplied by r2 sorry r1 d theta 1 multiplied by r2 d theta 2. So r1 d theta 1 multiplied by r2 d theta 2. This is the area of the membrane. So let us try to simplify it, considering that the angles are small. So for small angles, for small angles is d theta 1 sorry d theta 1 and d theta 2. So if we see here, we will see that cos of 90 minus d theta 1 by 2, this will be equal to sin d theta by 2, the sin d theta 1 by 2, and this similarly is equal to sin d theta 2 by 2. So for small angles, we know sin of the angle is nearly equal to the angle. So sin d theta 1 by 2 is nearly equal to d theta 1 by 2, and sin of d theta 2 by 2 is nearly equal to d theta 2 by 2. So we will just replace these values here in the equation that we have written previously. Sigma r2 d theta 2 into d theta 1 by 2 plus 2 sigma r1 d theta 1 into d theta 2 by 2. This is equal to pi minus po r1 d theta 1 r2 d theta 2. So this becomes equal to sigma uh, r1 d theta 1 plus r2 d theta 2 sorry it is sigma r1 d theta 1 d theta 2 plus R2 d theta 1 d theta 2. This is equal to delta P, that is the pressure difference, R1 R2 d theta 1 d theta 2. So the angles will be cancelled from both the sides, and we will reach this equation R1 plus R2 is equal to delta P R1 R2. So delta P is equal to sigma R1 plus R2 by R1 R2, or we can say that delta P is equal to sigma then 1 upon R1 plus 1 upon R2. So this is the equation for the pressure difference across a membrane separating two fluids. The expression for the pressure difference separating across a membrane separating two fluids. So if there is any doubt throughout the solution, you can ask. Then we will move on to the next problem. This is a very essential derivation, and we use it to find the pressure difference across many of the commonly encountered bodies, such as water droplets, bubbles, soap bubbles, then liquid jets. In case of liquid jet, one of the radius here will be infinity. Okay, so this is how we define what will be the pressure difference across such bodies. So if there is any doubt in any of this, you can ask. Okay, so I am taking that there is no doubt in this. So we will move on to the next problem. So which among the following statements is or are correct regarding the no slip boundary condition? So regarding the no slip boundary condition, so essentially what happens in the no slip boundary condition? Um, mm, it defines. So the at the solid, if a fluid is moving over a solid, then the at the point of contact there will be no relative tangential velocity. That is, we can say that suppose this is a solid and this is a fluid that is flowing on it. Then if we see that at the point of contact, at every point of contact between the solid and the liquid, since the solid or say this is the solid and this is the liquid molecule, the fluid particle here, then at the point when the fluid particle is in contact with the solid, in that case there will be no relative tangential velocity between the two. That is, if the solid is at rest, you can say that if the solid is at rest, then the fluid particle will also be at rest. If the solid is moving at some particular velocity, then the fluid particle will also have the velocity equal to the velocity of the solid. This is essential. This is concerning the tangential velocity. That is, along the interface between the solid and the liquid. But in the vertical direction, the velocity might exist, can exist, or you can say non-zero velocity can exist in the vertical direction. But in the that is in the tangential direction, there will be no relative velocity. This is the essence of the no slip boundary condition. So yeah, the option number A, that it represents zero relative tangential component of velocity between the fluid and the solid at their points of contact. So this is correct. That is, option number A is correct. No slip boundary condition implies that the tangential component of velocity between the fluid and the solid is zero at points of contact. So option number A is correct. Option number B, it states it represents zero relative normal component of velocity. So as I have stated that non-zero velocity can exist in the normal direction. So this is the option number B is not correct. Now see, it does not hold true if the fluid is a rarefied gas medium. So if the fluid is a rarefied gas medium, what will happen? So suppose these are the molecules of the fluid and it is rarefied. That is, the relative distance between the two molecules is very significantly large. In that case, the you see that the momentum exchange or the intermolecular force of attraction, which is in case of a rarefied gas medium, it is the momentum exchange. So for rarefied gas medium, this momentum exchange, if the particles are very far away from each other, then the So for a rarefied gas medium, when the particles are very far away from each other, the momentum exchange will not be sufficient. So if the momentum exchange is not sufficient, we cannot say that the fluid that is in contact with the solid is essentially at a state of rest. Okay, so because the for a rarefied gas medium there will be fewer collisions between molecules, so fewer collisions between molecules, which again implies that incomplete momentum exchange. So there no sleep condition does not hold. See, in case of when we are considering general fluid, whatever velocity might be at the surface, we will see that the velocity will keep on decreasing like this until it becomes zero in contact with the solid. This happens because of the viscosity of the fluid. But since we cannot be certain, and in case of gas, the viscosity comes from the momentum exchange. In case of rarefied gas medium, this momentum exchange will not be sufficient. So we cannot be certain about the role of the viscosity in case of a rarefied gas medium. That is why the no slip boundary condition does not hold good, or does not hold true in case of a rarefied gas medium. Okay, so option number C is also correct. Number C is also correct. So the correct options here will be option number A and option number C. So if there is any doubt in this, you can ask. Okay, so I am taking that there is no doubt in this. We will now move on to the next problem. So what is which among the following statements is true related to the Reynolds number? So yeah, Reynolds number, it is essentially defined as the ratio of the inertia force to the viscous force. Uh, it is a non-dimensionless number. Actually, one of the most important non-dimensional numbers that is prevalent or that is in use. So it defines. It also defines the transition it is used to define the transition at which the flow becomes from laminar to turbulent. So Reynolds number, this is inertia force by viscous force. What is the inertia force? Inertia force is mass multiplied by acceleration, right? And the viscous force is mu. If we have to find out the first, we can see the viscous stress. So it will be mu du or dv by dy, and so this is the viscous stress, and then we multiply it with the area to get the viscous force. Yeah. So this one multiplied by the area on which it is acting. Now we will consider this as so if we write it, so what is mass? Mass is density uh, multiplied by the volume, that we can write it as, let us write it as L cube. The just we are using the dimensions for the volume. So this is the mass multiplied by acceleration. Acceleration can be written as velocity and then dv by dx. Acceleration can be written as velocity dv by dx, right? So if we write the dimensions of here, or we can write it like this: v, dv is also v, and dx is L. For this one it is mu, dv is v, dy is L, and this is L square. So with simplification, what do we get here? Uh, in the numerator we have rho v square L square, and here we have mu v L. So with further simplification we get rho v L by mu. So this is basically the expression for the Reynolds number, rho v L. L is any characteristic length. L characteristic length. So for different bodies there will be different values of this characteristic length. And the correct option here is option number B. So coming to the next problem, which among the following statements is or are correct regarding the viscosity of liquids and gases? So uh, we know that for liquids, the viscosity is due to the intermolecular force of attraction between the molecules, and for gases, it is due to the momentum exchange. So we will take the cases individually. So for liquids, the viscosity arises due to intermolecular forces of attraction between the molecules. Now, with increasing temperature, sorry about that. Yes, so between the molecules, with increasing temperature, these intermolecular forces, the molecules will now move away from each other, and they or these intermolecular forces of attraction will decrease. Uh, the intermolecular forces of attraction decreases. Decreases. So, viscosity decreases with increasing temperature. So it is option number B. Similarly, for gases, the viscosity is due to the momentum exchange between the molecules. And see, we have already discussed. So, as the temperature increases, the kinetic energy of these gas molecules will increase because their speeds will increase. So, this momentum exchange will also increase with the increasing temperature. That is why the viscosity of gases increases with the increasing temperature. So this is option number D. So the correct options are option number, sorry, this is option number C and option number D. Yeah, so correct options are option number C and D. So if there is any doubt in this, you can ask. Okay, so I am taking that there is no doubt in this. We were moving on to the next problem. So we are asked to find the correct unit of kinematic viscosity. So what is kinematic viscosity? Kinematic viscosity is the ratio of the dynamic viscosity and the density of the fluid. So kinematic viscosity is equal to dynamic viscosity by rho. So what is the unit of um, mu here, or let us first start with the unit for mu. Then mu is what, minus tau du by dy. So if we take the dimensions of mu, then this will be dimension of tau and dimension of du by dy. So dimension of tau is ml inverse t to the power minus 2, and this one has a dimension of velocity, and this is the length. So we will get it here to be m L inverse T inverse. Therefore, kinematic viscosity, the dimension of kinematic viscosity will be m L inverse T inverse, and the dimension of density, that is m L to the power minus 3. So it will come out to be L square T inverse. So what is L square T inverse? It is meter square per second. Since there is no mass term in its unit, that is kg, that is the mass term, or the mass dimension is not present in this unit of viscosity, hence it is called kinematic and not dynamic. Okay, so the option is B. Now coming to the next problem, which among the following is the correct statement for flow over a flat plate? Flow is considered to be inviscid only outside the boundary layer. Flow is considered to be inviscid only inside the boundary layer. Flow is considered to be inviscid in the entire region above the flat plate. Flow is considered to be viscous in the entire region above the flat plate. So see, the why is the boundary layer formed basically? So the boundary layer is formed. So this is a solid, and the fluid enters this, starts flowing over this solid, and what happens is, because of the no slip boundary condition, the tangential velocity at the point of contact, this velocity it becomes zero. That is, this layer of the fluid does not flow. So this has a zero velocity, say. So this has zero velocity. Now, but this has a velocity of u, say u infinity. Then this one will keep on moving at u infinity. Or reverse, in a reverse way we can see. So this one will be at a velocity 0, but the particle just above it will be at a just higher velocity than 0. Similarly, the particle uh, above this will be at just somewhat higher, and this will keep on increasing. This will keep on increasing, and it will keep on increasing till the point of u infinity is reached. After that, it will remain only u infinity. So the point from this, from the surface, from the interface of the liquid and the solid, the point where we get this u infinity, or specifically 0.99 times of u infinity, that is 99% of the velocity, free stream velocity. U infinity is a free stream velocity, and if at the point where we get the 99% of that velocity, and throughout this length of the plate, if we um, draw, that is, if we connect all those points, we'll get a line that is called the boundary layer, and that is called the boundary layer. Okay. So this boundary layer, why is it formed? Because the fluid at this, or the fluid which is not moving at a contact with the solid, which is not moving, it is trying to pull back the fluid just above it. Similarly, that fluid particle is trying to pull back the fluid just above it. So in this way, the momentum or the velocity is transmitted, that is, the zero velocity of the solid plate is transmitted. Now, why is this coming? Because there is a viscosity of the fluid. So with the boundary layer is basically formed because of this viscous effect. So inside the boundary layer, we cannot assume the viscosity, the flow, to be inviscid. But outside the boundary layer, where there is no change in the velocity, we can consider the flow to be inviscid for its for the analysis of that region. But inside the boundary layer, we cannot consider the flow to be inviscid, because it is the viscosity itself that results in the formation of this boundary layer. So inside the boundary layer, the flow is viscous. Outside the boundary layer, the flow can be considered to be inviscid. So the correct option is option number A. Okay. So if there is any doubt in this, you can ask. Okay, so I'm taking that there is no doubt. So we will move on to the next problem. Which among the following is the correct expression for the apparent viscosity? So what is apparent viscosity? So uh, before going there, so there is something, some fluids are for which the stress strain behavior is linear. Those are called the Newtonian fluids. For some fluids, for which are called the non-Newtonian fluids, we get the apparent viscosity, we get the shear stress in this form, du by dy to the power k, and there can be or may not be an intercept here. Okay, so um, if we write it in this form, du by dy to the power k minus 1 multiplied by du by dy, and we denote this form as mu apparent, or this one, then it takes the form of the uh, uh, the same form as the Newtonian fluids, but the mu here is also dependent on the rate of deformation, and mu a is mu du by dy to the power k minus 1. So this is the apparent viscosity, and this viscosity depends on the value of the um, it depends on the rate of deformation as well as this value k, that is a flow consistency index. So or sorry, so it's the flow behavior index. Just there has been an issue with the symbols. So yeah, so this is k and this is n. This is k, this is n minus 1, this is k, and this is n minus 1. So n is the flow behavior index and k is the flow consistency index. And this apparent viscosity also depends on the rate of deformation, unlike the Newtonian phase where the viscosity is independent of the deformation, rate of deformation. So the correct option here will be option number D. Now for this, which among the following statements is correct regarding thixotropic and rheopectic fluids? So can anybody just tell me which is can anybody give me an example of a thixotropic fluid? It is very commonly used. So examples of thixotropic fluids are like ketchup, toothpaste, shaving cream. So these are the examples of thixotropic fluids, and example of rheopectic fluids are like printer, the ink that we use in the printers. That is the example of rheopectic fluid. So if we draw the stress strain behavior of thixotropic and rheopectic fluids, we will see it something like this. This is thixotropic, and this will be rheopectic. Now, with time, how does these values decrease? The apparent viscosity and the shear stress, that is this value. So the shear stress for thixotropic and rheopectic fluids. So for rheopectic fluids, the shear stress value it increases with time. And uh, this one, this is the thixotropic fluid. Sorry, this is thixotropic fluid. So with time, the shear stress or the shear deformation, this value du by dy is or the shear stress value it is decreasing, or for thixotropic and for increasing for rheopectic fluid. So this even the apparent viscosity, which is a function of the deformation, so the apparent viscosity, which we can write it as k du by dy to the power n minus 1. So since mm, the shear stress it is also with the with time this for the thixotropic fluid the shear stress decreases, and for rheopectic fluid the shear stress increases. So if we write the expression for shear stress, what is it? It is k du by dy number n minus 1 and du by dy. So this value, the apparent viscosity, it will also uh, follow the similar variation with time. That is the apparent viscosity, it will also for thixotropic, thixotropic, TH, apparent viscosity decreases with time, and for rheopectic, apparent viscosity increases with time. Okay, so the correct option is option number A. This is just based on the their behavior that has been observed. Okay, so coming to the next problem, a body weighing 500 newtons slides down a uniform speed of 2 meters per second along a lubricated inclined plane, making a 30-degree angle with the horizontal. The viscosity of the lubricant is 0.1 kg per meter second, and the contact area of the body is 0.25 uh, meter square. And determine the lubricant thickness assuming linear velocity distribution. You see, what is the problem here? This is a inclined plane making an angle of 30-degree, and there is a layer of lubricant on it. See, this is the lubricant layer, Okay, and with this lubricant, a body that has a weight of 500 Newton, it is sliding down at a velocity of 2 meters per second. Okay, so determine the lubricant thickness assuming linear velocity distribution. So if we that is, what is linear velocity distribution? So if we enlarge it, so this is the solid, this is the body, and this is the solid, and this is the fluid. So in the fluid there will be, so this is the fluid, right, that it will be near so this layer, it is moving at 2 meters per second, and this will be at a zero velocity, and there will be linear variation from 0 to 2 meters per second. So if we apply the Newton's law of viscosity here, uh, so it is tau is equal to mu du by dy. Okay, what is tau? Tau is the force per unit area, right? So this is force per unit area is equal to mu du by dy. What is the force here? The force of 500 Newton, it is not totally responsible. A component of this, which is say this is one component and this is another component. So this component will be this angle is 30 degree. So this angle is 500 cos 30, and this is 500 sin 30. So 500 sin 30 is what is responsible for the motion. So 500 sin 30 500 sin 30, the area of contact between the two is 0.25 meter square. The viscosity is 0.1 kg per meter second. And what is du? You can say for a that is the slope of u, that is du by dy. So the change in velocity that is happening in this, the change in velocity that is happening in this change in y. So the change in y is what we have to find. That let us denote it as h. Say this is h, that is the lubricant thickness. And what is the velocity change? Velocity change is from 2 to 0. So what is the value of h? H is 0.1 into 2 into 0.25 by 500 sine 30. So sine 30 is essentially half. So we will get this value to be 0.0002 meters or 0.2 millimeters. So 0.2 millimeters is the thickness of the lubrication that is required for a for the body to be moving down at this velocity. So if there is any doubt in this, you can ask. Okay, so I'm taking that there is no doubt. So we will continue with the next problem now. So from the following test data, determine the bulk modulus of elasticity of water. So the data has been given, that the pressure value and the volume at one test point, and the pressure value and the volume at another test point. So we have to determine what is the bulk modulus of elasticity. So the bulk modulus of elasticity, it is essentially denoted as K. So minus V delta P and delta V. So what is delta P here? Delta P is 12 minus 3.5 meganewton per meter square. So this is 8.5 into 10 to the power 6 Pascal. And what is delta V? Be careful to see that whatever pressure value you are taking first should correspond to the volume value you are taking first. So this will be 0.99 minus 1, and that is 0.01 meter cube. So the bulk modulus value K is, what is the initial volume? Initial volume is 1 multiplied by delta P, that is 8.5 into 10 to the power 6, and this will be minus 0.01. So it will come out to be 0.85 into 10 to the power 9 Newton per meter square, which is option number B. So coming to the next problem, this is a problem related to the gas bubbles. So using the derivation that we have done in initially, this derivation and this result, can you try to solve this problem? Just try to solve this problem, in just try to proceed with this problem at least in around 2 to 3 minutes. Okay, so how to go about this problem? so small gas bubble. Okay, so on both the surfaces there is like whatever gas bubble it is forming, this is the gas bubble, then on both the sides there will be some different fluid. Okay, so there are two surfaces. So the pressure differences, so there will be, this is one surface and this is one surface, two surfaces will be 2 multiplied by, what is it, sigma 1 by r1 plus 1 by r2, 2 into sigma 1 by r1 plus 1 by r2. So for a gas bubble, for gas bubble r1 is equal to r2, so this becomes 2 sigma into 2 by say r, that is the radius, or 4 sigma by r. So what is 4 sigma, what is given as 0.0728, and the diameter is 0.2, so this will be, radius will be 0.1 into 10 to the power minus 3. This is in millimeters, so we are taking it to meters. So this will come out to be 2912 Pascal or 2.91 kilopascal. That is option number D. Okay, so if there is any doubt you can ask. Okay, so going to the next problem, an atomizer forms water droplets. So what is the difference here? For water droplet, only one surface is exposed to air. This is filled with water itself. So only one surface is filled with is exposed to the surrounding fluid, say air. So for this, delta P will just be sigma 1 upon R1 plus 1 upon R2. So we have to determine what is the pressure inside. If the pressure within the droplets is 102 kPa, we have to determine what is the pressure outside the droplets. So inside the droplets, okay. So inside the droplets, why is it not working? Yes. So inside the droplets there is one pressure Pi, and outside the droplets there is another pressure Po. So the pressure Pi, it has been given as 102 kPa. Po we have to determine, and the diameter of the water droplet is 10 into 10 to the power minus 5 meters. So the radius will be, which is essentially equal to R1 and R2, is equal to 5 into 10 to the power minus 5 meters, and the surface tension has been given as 0.0728 newtons per meter. So delta P for here, there is only one surface, so it will only be 1, and that is sigma 1 multiplied by sigma 1 upon r1 plus 1 upon r2, where r1 equals to r2, so this will be 2 sigma by r. 2 into 0.0728 by what is the radius, 5 into 10 to the power minus 5. So the value comes out to be 2912 Pascal or 2912 Pascal or 2.91 kPa. And so delta P is, which is essentially equal to Pi minus Po, that is equal to 2.91. So P outside that we are required to find is Pi minus 2.91, that is 102 minus 2.91, and it will come out to be 99.09 kPa. That is option number C. If there is any doubt in this, you can ask. So, so coming to the next problem. So we have been so this is a liquid droplet on a solid surface. So there are different interfaces here: the solid with vapor, the liquid with vapor, and the liquid with solid. So in equilibrium of all these three surface tension forces acting, there will be this this angle, the contact angle will be defined. So how will we go about this? We'll essentially do a force balance. So this is the solid surface, okay, and this is the liquid on it. This contact angle theta we have to determine. So this is the liquid, this is the vapor, and this is the solid. And right, it has. So this is the surface tension force between liquid and vapor. Then there from this surface there will be surface tension between the vapor and the solid, and in between the two there will be at this interface there will be another surface tension, that is sigma between the liquid and the solid. So force balance along the horizontal direction force balance in the horizontal direction we do, then it will be same sigma. We are taking the right hand side to be positive, so sigma ls plus sigma lv cos theta. This will be equal to sigma vs. So sigma lv cos theta is equal to sigma vs minus sigma ls. Therefore theta will be cos inverse sigma vs minus sigma ls by sigma lv. So see, if we just know the surface tension coefficient between the components, we can just determine what will be the contact angle. So this is essentially option number C. No, it is option number D. Okay, so if there is any doubt in this, you can ask. Okay, so we move on to the next problem. Uh, Determine the excess pressure in a cylindrical liquid jet over the pressure of the surrounding atmosphere. So see, that is what I was saying, that the initial result in problem number 1 that we have defined, it can be used to in n number of cases for calculating the pressure difference between such bodies. So here one of the body is a liquid jet, cylindrical liquid jet. So say this is the liquid jet, a section of the liquid jet. One of the radius is r1, and what will be the other radius? The other radius will essentially be infinity. So this is pi, this is po, and delta p is equal to sigma 1 upon r1 plus 1 upon r2. Say the radius is r. So here r1 is equal to r and r2 is infinity. So if we put the values here, it will be delta p equals sigma 1 by r plus 1 upon infinity. This becomes 0. So it will just be sigma by r. That is only the radius of the cylindrical jet, the single radius of the cylindrical jet define what will be and the surface tension, of course, it will define what will be the pressure difference between the liquid jet and the surrounding pressure. Okay, so this is the option number C. If there is any doubt in this, you can ask. Okay. So let's move on to the next problem. A vertically clean glass piezometer has an inside diameter of 0.5 millimeter. When a pressure is applied, water at 20 degrees Celsius rises into the tube to a height of 25 centimeter. It is given that the surface tension of water is 0.0728 newtons per meter. The contact angle theta is 0 degree. Density of water is 1000 kg per meter cube and the acceleration due to gravity is 9.8 meters per second square. Determine the capillary rise in the tube. So for this, we will be using a result that we have already derived in the previous class. So what essentially is the problem here? So this is the, say, the liquid. In this liquid we insert a glass piezometer here. So the liquid so there is also a pressure applied here, P, say this is P, and the liquid rises to a height of 25 centimeters. This height is this rise in the fluid is due to both the applied pressure and the capillary rise. The diameter of the tube is 0.5 millimeters. So we have to determine what is the first we have to determine what is the capillary rise in the tube. So the capillary for the capillary rise in the tube, H, we'll use the formula for sigma cos theta by rho g d, where d is the diameter of the tube. So this result we have already derived in previous TA session. Okay. So if you have any doubt in that, you can just go back and see that derivation. And so here the contact angle theta is given as 0 degree, uh, sigma is 0.0728, cos of 0 degree, that is 1, it will come, and density is 1000, to G is 9.8, and D is essentially the diameter, that is 0.5 into 10 to the power minus 3. So we get this to be 0.06 meters. 0.06 meters, or this is equal to 6 centimeter. So the correct option is option number A. Okay, so here I would also like to mention, so how to know when the capillary rise will be significant. See, as we this rise in the capillary due to capillarity, it is inversely proportional to diameter, that is H is inversely proportional to diameter. So as the tube diameter increases, keeps on increasing, the rise in the capillary tube will keep on decreasing. So this rise in the capillary tube is significant only for very small diameter tubes. Okay, also if the surface tension increases, then the rise will increase, and if the density of the fluid increases, then the surface tension will decrease. So the rise in capillary tube is significant only for small diameter tubes. Okay. Now coming to the next problem, in the previous problem estimate what is the applied pressure. So see, the total rise in the capillary tube is rise in the, not the capillary tube, rise in the piezometer tube is 25 centimeter. This rise is a result of the pressure applied as well as the capillary rise. So this 25 centimeter we can say, or is 25 total rise is equal to rise due to pressure applied plus rise due to capillarity. So the total rise is 25 centimeters, rise due to pressure plus the rise due to capillarity is 6 centimeters. So the rise due to pressure, that is the pressure applied, is 19 centimeters. That is 19 into 10 to the power, or we can write it as 0.19 meters. But what is the rise due to pressure? It will be equal to so due to this pressure, this rise is happening. Okay, so how will we calculate this? How will we relate this? So this applied pressure will be equivalent to this rise. Rise due to pressure is 0.19 meter, and so equivalent applied pressure is what? So rise this, let us say, as H. So then the equivalent applied pressure will be is P, that is equal to rho GH. So whenever so if the pressure P, let us consider any pressure P, then it can be identified with the rise of a fluid by the term rho gh by equating it to rho gh, where rho is the density of the fluid and h is the height to which the fluid is rising. So if the rise due to pressure is 0.19 meter and the fluid that we are considering has a density of rho, then the applied pressure due to which this rise has occurred can be equated as rho gh. So what is rho here? Rho is 1000 into 9.81 into 0.19, and this comes out to be equal to 1862 Pascal. That is option number B. So if there is any doubt in this, you can ask. Okay, so I am taking that there is no doubt. Let us move on to the next problem. So a manometer is formed from a glass tubing with uniform inside diameter of 6.35 millimeter as shown in the figure below. So this is the diagram of a manometer which is used to measure the pressure or the pressure difference in the pipelines. The U-tube is partially filled with water. So this is essentially water. Uh, this is essentially water, and this is on top, and oil has been put inside. Volume of the oil that is added is 3.25 centimeters cube. Assume that both the legs of the U-tube are open to the atmosphere. Which among the following relationships is or are correct regarding the pressure? So mm, A, C, B, and A and C. So A and C, the points A and C are both exposed to the atmosphere. The points A and C are exposed, both exposed to atmosphere. So this PA is equal to PC is equal to P atmosphere. That is option number A is correct. Now PB equals to PD. See, B and D are the fluids, are the points. The points B and D are at the same level of the same manometric fluid, that is water. So B and D. So if the oil was still here and the point B was here is the same thing, then the points B and D would not have equal pressure. But since both the points B and D are lying at the same vertical level of the same manometric fluid, that is why they will be having the same pressure. B and D are the points B and D are at the same level, same vertical level of the same manometric fluid. So P pressure at B is equal to pressure at D. That is option number B is also correct. Now A and D, they are not equal because the pressure at A is not equal to pressure at D, because see, pressure at A is equal to pressure at C, and the D is lying below C. So it will be definitely at a higher different pressure. Similarly, PB equals to PC is also not the case because for the same manometric fluid, B and C are in the same manometric fluid, but C is at a higher level than B. That is why B and C will not be at the same pressure. And PB is not equal to PC. So the correct options are A and B. Now, going to the next problem. In the previous problem, which among the following expressions are correct? So PB equals to PA. Is PB equals to PA? No. It is A and B are in the manometric fluid of oil. If we consider, then B is at a different. B is lower than the point A. That is why it will be at a different pressure. So PB is not equal to PA. But PB minus PA will be, there will be a particular pressure difference. What is it? PB is actually greater than PA, and PB minus PA will be equal to what? This is the oil. So this pressure difference from A to B, that is delta P AB, and this is equal to density of the oil multiplied by G multiplied by the length from A to B, that is L. So the option number B is correct. Then again PC is not equal to PD. Again PD is greater than PC, and PD minus PC will be equal to what? It will be equal to, this is water. C and D are both in water. The points connected, these points are connected by the fluid water. So this will be delta PC to D, or density of water multiplied by G multiplied by L minus H here. So this is option number D. So the correct options here are B and D. Now, going to the last problem for today. In this previous scenario, we have to calculate the equilibrium height. It is given that the specific gravity of the oil is 0.827. So how will we go about this? See, first the specific gravity of oil has been given. So specific gravity is equal to 0.827. Therefore density of oil will be 827 kg per meter cube. If we draw the manometer again here, so the point C, we actually have to determine this height H. Say this is oil and this is say water. Now, what is L? L we can determine from the volume of the oil that has been put in. So the volume of the oil is given as 3.25 centimeter cube. So the volume of the oil has been given as 3.25 centimeter cube. This is oil volume is 3.25 centimeter cube. So if we use this data, now the volume of oil is equal to 3.25 centimeter cube, and what we have so how do we find the volume? It will be rho sorry, it will be pi by 4 d square into this L. So pi by 4 into d square into L will be equal to 3.25 centimeter cube. So d is in millimeter, so let's take this centimeter cube to millimeter, so this will be into 1000 millimeter cube, and therefore the L is 3250 into 4 by pi into d square, where d is given as 6.35 square. So what is this value? So it is 102.62 millimeter. 102.62 millimeters. Now, what we have seen previously, we have seen that let me just write the points also here. This is A, this is A, this is B. So the pressure at B is equal to pressure at D, we have got, right? Because they are in the same height of the same manometric fluid. Now we use this. This implies pressure at A plus density of oil into G into L. Okay, that we have found from this problem. So pressure at B is equal to pressure at A plus rho oil G into L is equal to pressure at C plus density of water into G into L minus H. But pressure at A is equal to pressure at C. Therefore, density of oil, so this gets cancelled from both sides. So into G into L is equal to rho water into G into L minus H. So G also gets cancelled. We have to determine H. So rho oil by rho water is equal to 1 minus H by L. Therefore, H upon L is equal to 1 minus, and this is the basically the specific gravity of oil, that is 0.827. So this is what is it? It is 0.173, and what have we got L to be? 102.62. So 0.173 into 102.62, that is 17.75 millimeters, which is the option number C. So if there is any doubt, you can ask, or else we will close today's session. Okay, so I am taking that there is no doubt. So we are closing today's session. Uh, mm, Thank you for attending, and please attend the next session due Friday, next Friday from 6 to 8. You may leave. Thank you.